Right, and now the final talk of the session is Michael Pereira, who's going to talk about evidence accumulation and conscious access. So please, yeah, take it away, Michael.
So hi, everybody. I'm Michael Pereira, and I'm going to happily continue with evidence accumulation and attempt to link it to conscious access using single neurons and computational modeling. So imagine that you're bitten by a mosquito. So there is a conscious experience that is associated to this event, and our goal is to find the brain processes that support this conscious experience. And so for this, we're going to use a contrastive approach, meaning that we take stimuli that for the same physical properties sometimes do not lead to a conscious experience. So for example, you could not notice that you've been bitten by a mosquito. And so that allows us to contrast the brain activity between the two conditions, and the difference will correlate with the conscious experience. And that's why they're called the neural correlates of consciousness. And so how do we probe what's the content of the conscious experience? Well, the good thing with working with humans is that you can ask them. And so if they answer that they felt the stimulus, then it's a hit. Otherwise, it's a miss. And this is a first order report because it's directly related to the stimulus. And we're also interested in second order representations, so representations of oneself in a first order state. And as a proxy to this kind of processes, we will use confidence ratings. We will ask the participants how confident they are about their first order reports. And so there have been many studies of the neural correlates of consciousness. And here we're trying to tackle a hypothesis that tries to explain how this brain activity relates to conscious experience, and it's based on mechanisms that a mechanism that's borrowed from the field of decision making. And so the idea that some neurons in your brain accumulate noisy perceptual evidence over time, and when it reaches a bound, you take decision. And so since this process is stochastic, this could happen at different timings, or it could not happen at all. And in this case, it's a miss. And so this has been extensively studied in non-human primates, also in humans using EEG, and linked to consciousness. And so in this study, we're going to link it to consciousness using single neurons and attempt to link evidence accumulation to confidence and to a computational model. And so we were lucky to be able to work with a patient with epilepsy that was implanted with a microarray in the posterior parietal cortex here. And just, so here you see the microelectrode array, and it was just next to the somatosensory area. So that's why we're going to look at tactile perception. And so with these participants, we did 3 experiments. And the first one, so we apply weak vibrotactile stimuli on the wrist of the patient. And we titrate the intensity so that in 50% of the cases, the participant will not report feeling the stimulus. And in 50% of the cases, he will feel it and immediately press a button. So we get the response time. And so this would be a hit. And so for the analysis, we time lock on the stimulus onset, and we're going to count the number of times that the neuron fires in this in a window between 500 milliseconds and 5 seconds. And we're also going to look at the firing rate. So here's the firing rate for these neurons that we believe accumulate evidence. So you see this rather typical buildup of the firing rate prior to the response. So here you have 3 bins of response times. And you see that the slope is steeper for faster responses. And so the way we select these evidence accumulation neurons from the other neurons, so first we look at detection neurons, so neurons that have a different firing rate for hits and misses. And then from these detection neurons, we look at the ones that have this gradual build up to the response time. And so we found 12 of them, and these numbers, they're statistically significant, meaning that we checked that we couldn't have obtained them by chance. Now, the problem with this experiment, of course, is that the neural correlates of consciousness are contaminated by the fact that there was a motor response in one case and not for misses. And so in the second experiment, we used the start cue, and that was followed by a 2-second window where the stimulus onset could occur at any moment. And importantly, then we added a 1-second delay before the participant was cued to report whether he felt the stimulus or not, and his confidence about his response. And so here we have two factors. We have the detection, hits versus misses, and we have the confidence. And so we looked at these two factors in a factorial analysis, and we actually found that most of the neurons that were responsive, they were responsive to both factors, meaning that there were 17 neurons that showed detection times confidence effect. So showing that it's probable that the information that is used for detection could also be used for the confidence in hits. And here you see the average firing rate of these neurons with this ramp up of the activity that you can see only for high confidence hits. So now the thing is that these two experiments, they were always accompanied with this decision making. So we were asking the participants to report whether they felt the stimulus or not. So it's somehow hard to disentangle whether this is related to decision making or to conscious perception by itself. And so in the third experiment, we stimulated the patient with stimuli with different intensities, and we didn't ask him to report anything. And although we didn't ask him to report anything, we still found some neurons that had that coded for the intensity. So with higher intensity leading to higher firing rates. And so now we characterized these neurons in the parietal cortex, and we were interested in seeing whether we can model this neural and behavioral responses using a computational model of evidence accumulation. So for this, we recorded 18 healthy participants with EEG, and we found this famous CPP here that is actually quite like the neural responses that we got, meaning that there's an increase for hits and not so much for misses. And you see here the behavior with the detection rate and false alarm rate. Now, the problem with fitting these evidence accumulation models is that usually you fit them to discrimination task and you have response times for all conditions. Here we can't get response times for misses. And so we decided to not collect any response time. So we're not contaminating this NCC, but we fit the shape of the evidence accumulation to the neural response for hits and for misses, while keeping the simulated behavior identical to the observed behavior. So here you see the results of the fit for all the subjects and the behavior, and you see that even for single subjects, it does a decent job at capturing the individual differences. And so now that we have this first order model, we're going to fix the parameters and try to simulate confidence. And so for this, we're going to simulate traces of evidence accumulation, and we're going to define confidence as the maximum of the accumulated evidence over time with respect to the boundary. And that allows us to also define confidence for misses as this distance or for correct rejection. And so using this mechanism of maximal evidence for confidence, we were able to reproduce the confidence, so meaning here you see the average confidence for these three conditions: hits, misses, and correct rejections over all subjects. And here you see the distributions of the confidence with with the model predictions, or model fits rather. And so we did a bunch of other tests to verify the predictions of the model, which are in the preprint if you're interested. But the last thing I wanted to present is that when we use this maximal evidence method to compute confidence while looking at our neuronal data from the patient, we were able to decode confidence for both hits and misses, while when we would apply the, let's say, more standard procedure of looking at time locking to the stimulus onset, we could not decode confidence for misses. So altogether, we present an evidence accumulation account of perceptual consciousness that's based on neuronal activity in the PPC and a computational model. And we think that this evidence accumulation account could also underlie perception in the absence of decision-making. And we also propose a way to explain metacognition also in the absence of awareness. And finally, this evidence accumulation account is integrated in the global workspace theory, because it has already been hypothesized that the ignition in the global workspace theory is triggered by accumulated evidence reaching a boundary. And so with this, I'd like to thank all the co-authors and the funding agencies and the audience for their attention, assuming I'm not alone. Thank you.
Thank you, Michael. And I can confirm you're not alone. There's quite a lot of people in the session, actually. Yeah, okay, so we have a question from Nadine, which is actually pretty similar to what I was going to ask. So let's go ahead and ask that one. So Nadine says, thank you for the interesting talk. Great stuff and very clear effects. The one thing I was unsure about was, why did you frame this as a consciousness study? To me, it seems like traditional perceptual decision-making study with a metacognitive component. You find effects of detection, response, stimulus intensity, and confidence rating. What makes it specific to consciousness?
Yeah, sure. So, well, the thing that, so we're interested in linking it to consciousness. So of course, there are a lot of questions that come into play that are, I guess, rather typical to works in consciousness, but we think that the fact that we titrate the intensity to get 50 to 50% hits and misses, and the fact that we just ask the subject whether they perceive the stimulus or not. I mean, unlike animal studies where you're never really sure what is the corresponding perception, we think that this allows us to, let's say, at least tentatively link it to consciousness. But I understand your concern.
Yeah, I mean, I guess consciousness is always a tricky issue in that sense.
That's also why we talk about conscious access and not directly consciousness in the title.
Right, yeah, try and be a bit safer. I mean, so it's actually my question was a bit like that. So is the bigger picture question here, like, sorry, the bigger view of consciousness here is that somehow we're always accumulating evidence about the world, and it's only when that evidence reaches some threshold that we become conscious of it. Is that more? I'm quite naive about consciousness stuff, so I'm just trying to get a feel for it. Is that the sort of the idea behind what you're doing here, or?
Yes, so that would be very much linked to this global workspace theories. Of course, there are many other theories, and there's no consensus on whether this is actually the theory.
Okay. Right.
But let's say in our view and in our model, let's say that's what we would propose.
Cool. All right, we have time just about for one more quick question, I think. So we have Derby has asked, very interesting talk. I couldn't quite follow this, but was it true that there were many neurons in experiment 1 that showed difference between hits and misses, but did not show an evidence accumulation profile?
Yes, that's true. They were actually, so one thing we have to say is that so the conditions to say that neurons were accumulating evidence were pretty strict, because we really wanted to see this gradual buildup. And so that's why we found actually quite few of them. But actually, when you look at all the neurons that respond to hits versus misses, it's very, very heterogeneous. So you see some that respond after the response, some that respond before, and with various shapes. So it's yeah, it's true that for the rest of the neurons, let's say we wouldn't have, let's say, any mechanistic explanation about what they're doing and what is their role.
Cool. All right. Well, in that case, I think we're pretty much out of time. We've got 1 minute before we get brutally cut off. So I'll just like to say thank you again to Michael, and thank you to all of our speakers in this session. That was really interesting. I hope everyone enjoyed that as much as I did. And yeah, if you want to follow up with further questions, unfortunately.